So in this video, we will start looking at trigonometric substitutions. So basically, excuse me, what we mean by trigonometric substitutions is we're not actually integrating per se trigonometric integrals, which we've done in previous videos. But here, what we mean by trigonometric substitution is we will be looking at, for instance, when one looks for the area of a circle or an ellipse. So for instance, if we were to look at the here, for instance, with radius a. So if this was radius a, then this is your x-axis and this is your y-axis. So then what would happen is you'd get y squared plus x squared equals a squared, which we know is the equation of a circle, which can be written as y is equal to the square root of, which is y is equal to a squared minus x squared. So basically, this half semicircle that you see on the top is actually this equation. Okay, the circle would of course be the complete this missing part, which I have not drawn in. Okay, which is this this equation here. But the one that I have drawn here, this semicircle, this equation is y equals a squared minus x squared. Now we know for a fact that if we were to find the area of this half circle, this integral is not an easy one to do. The reason being that if we had an x here, it would be a piece of cake. But since, in other words, what I'm saying is, if we had just something like this times x dx, that would make this a very easy integral to work out. But since we don't, it's not easy to actually work this out. So but there is a way we can actually resolve this square root, because if you think about it, it's this square root here that is really the problem. If we could get rid of the square root, we could go somewhere with this. So one way to get over this is to think about it in trigonometric terms. So if we look at this angle theta here, if we look at it from that perspective, and drop this perpendicular, then what we're trying to say basically is that essentially this distance here is a, of course, and of course this distance there would be x and y, of course, assuming here this is the coordinates are x and y. So now if I look at this, what we're saying is that basically sine theta is equal to x over a, which means x is equal to a sine theta, right? So if I use this substitution, then clearly you can see that this will resolve my integral, because then y, of course, is going to be equal to cosine theta. And that's how, in fact, if you substitute that in here, this in here, it gives you the connection between these two. So basically what I'm trying to say is that this gives rise to this very nice substitution, x equals a sine theta, or x over a equals sine theta, whichever one you prefer. Okay, and basically using this substitution, so let's follow through and see what happens. So dx then of course is equal to a cos theta d theta. So then what happens is dx is equal to a cos theta d theta, and as we substitute, the integral becomes the square root of a squared minus a squared sine squared theta, and then we have of course the a cosine theta instead of the dx. Okay, then you take the a squared out, and basically, let's do it slowly. So we'll have square root of, take the a squared out, 1 minus sine squared theta, and then of course we'd have the, we'll take this a out here. So that leaves us with a cosine theta d theta. Now, simplify further, this a squared here is under the root, so it'll slip out of the root, I'm sorry, here. it'll slip out of the root and we'll get an a squared outside, and then we'll have the square root of 1 minus sine squared theta, which, as you know, okay, is, we know the sine squared theta plus cos squared theta equals 1. So therefore, cos squared theta, sine squared theta, sine squared theta. So that means this will become just the square root of cos squared theta. We have the cos theta here and d theta, of course. So that will further simplify then. The a squared is there. Cos squared theta under the root is just cos theta times the cos theta makes this cosine squared theta d theta. And that's where we now can use another trigonometric substitution. So let me bring back the, let me just highlight, we're using this one, of course, which you can clearly see. And we're using, we now can actually use this one. Okay, so we're going to use here, basically, this integral then becomes a squared is outside, and we've got inside the cosine squared theta becomes a half, okay, and d theta. So this is going to be equal to, in fact, the a squared over 2, and then we'll have the integral here will be theta, plus there'll be a 1 over 2 here, and sine 2 theta. We'll add the constant later. Now as we go to convert this, change back the variable, that is. Theta is no other option but to say, of course, sine inverse of x over a, and plus this one, on the other hand, we'll have to convert this. So we're going to make this into 2, this is remember 2 sine theta cos theta. So the 2 will cancel with it, so it'll be just sine theta cos theta. Now sine theta, remember is just x over a, so this will be, this part will be x over a, and it'll be multiplied by this cosine theta. Now cosine theta, remember, is square root of 1 minus sine squared theta, which is square root of 1 minus x squared over a squared. So that's going to be this thing multiplied by 1 minus x squared over a squared, and that'll close the bracket, plus the constancy. So that's basically how we would convert it back. So you'll have you have basically 2 sine theta cos theta, and the sine theta is straightforward enough, it's x over a, and the other one basically is the cos theta, which is square root of 1 minus, as you see here. There it is. So remember, sine theta here, from this you can see sine theta is x over a. Okay, so we also know that, by the way, okay, the other way is you could go back to the triangle and calculate what cos theta would be directly as well, and you will find, of course, a similar answer in the end. So I would stick with this. It's quick enough to work out. Right, so now let's have a look at this other trigonometric identity. Secant squared theta equals, or secant squared a equals 1 plus tan squared a, can also be used to resolve certain types of square roots. So for instance here, if we were to look at, for the sake of argument, something like, instead of a squared minus x squared, if I had a squared plus x squared, for the sake of argument, then you can see that the a squared plus x squared, one could easily use x equals a, tan theta, and that would lead to, basically, if I substitute that in here, then I would get the square root of a squared plus a squared tan squared theta, and of course that, take the a out like before, and that will leave you with 1 plus tan squared theta inside here, and that would equal a sec theta. So you see the square root again gets resolved. Similarly, Similarly, for the same trigonometric identity, we can actually get two different types of square roots resolved. Here's another one. This is the third and other possibility is x squared minus a squared. Now in this case, again, a substitution of x equals, so this time a substitution of x equals secant theta. So if I were to use x equals secant theta, then I would get here, a secant theta, pardon me. So that would give me a squared secant squared theta minus a squared, which would then mean the a would again go outside, leaving a secant squared theta minus 1 under the root, and that would lead to just an a tan theta, because secant squared theta minus 1, clearly secant squared theta minus 1 is tan squared theta, and the root of tan squared theta is tan theta. So basically that covers all the possibilities that we could resolve these square roots using these two trigonometric identities that identified here, highlighted here. So let me summarize. So here I have summarized for you basically the three square roots that can be resolved using these identities on the right that you see here. And you can see here the substitution x equals a sine theta. Here the substitution equals x equals a tan theta, and in this one x equals a secant theta. And these would actually resolve the square roots that you see here. So we'll stop here. Thank you.